Hi, my name's Saffron and today I'll be presenting on Unit 8, the electromagnetic spectrum. Within my presentation I'll be discussing the principles and properties of types of electromagnetic waves, the properties of microwaves and infrared using selected examples, the uses and hazards of X-rays in medical applications. Also, I will be comparing and contrasting the properties of visible and UV light, with also explaining some of their applications, and also explaining the biohazards of ultraviolet and infrared radiation and their main effects. First, I'll be discussing the principles and properties of electromagnetic waves. Electromagnetic waves travel at a velocity of 300 million meters per second to -1. They have a range of frequencies and wavelengths called the electromagnetic spectrum. So here I have a picture of the electromagnetic spectrum. It goes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. As you can see here, this end at radio waves is lower energy with longer wavelength and low frequencies, whereas at this end is a higher frequency, shorter wavelength and higher energy at gamma rays. The human eye can only detect a section of the electromagnetic spectrum, which is the visible light spectrum. And here is a table of the electromagnetic spectrum, and this just gives you an idea of the approximate wavelength ranges of each of them and also their frequency range. Here you'll see that there is an oscillating magnetic field and an oscillating electric field. They are both inextricably linked and you can't have one without the other. Combined, these moving fields of energy can move electrically and magnetically charged particles. So here we have the electromagnetic wave and here's the magnetic wave. So we'll be discussing the properties of waves. Here's a diagram that I made myself. So you can see here, this is the crest of a wave. This is the trough of our wave. This is the amplitude, so it's from the baseline to the peak, or it could be from the baseline to the trough. And a wavelength is trough to trough or crest to crest. So amplitude, given the notation big A, is the maximum displacement of a particle in the wave from its equilibrium position, and it's measured in meters. Wavelength, represented by lambda, is the distance between points on its successive oscillations of the wave that are in phase, also measured in meters. And frequency is the number of peaks per second, measured in hertz, and velocity is the distance travelled by wave in 1 second, measured in meters per second. So we have something called the wave equation, which is velocity equals frequency times wavelength. So you can also put this within a triangle where you've got velocity at the top and frequency and wavelength, and therefore if you covered one of them you would know whether to divide one by the other to get this one or to times them both. Frequency and wavelength are inversely proportional, so therefore higher frequency equals a shorter wavelength and lower frequency equals a longer wavelength. And in regard to amplitude, obviously within music, if you turn the music up, you would have a higher amplitude as it has more energy. Or in the sea, a higher wave equals a more powerful and stronger wave as it has more energy. In electromagnetic radiation, amplitude is a measure of its intensity or brightness if on the spectrum of visible light. Now moving on to infrared radiation. Infrared radiation occupies a band of the spectrum from 700 nanometers to about 1 millimeter wavelength. Objects that are given off heat are emitting infrared radiation. Humans cannot see infrared radiation, however thermal sensors can measure and display infrared radiation. So for example, if you went into the Science Museum in London, they have a projector that you stand in front of and it has a camera that will detect your infrared radiation and then display it within the projector so you can see yourself in regards to your infrared radiation. Thermal imaging can be used on buildings to detect excessive heat loss so that they can patch it up so that all the heat stays in the building. It's also used in cameras for many home security systems. Also used in many handheld short range control systems such as TV remote. It's also used in remote control toys. Signal strength depends on the transmitter. Usually in households it's about 1 meter. And it must be a direct line of sight. It cannot pass through walls, however it can be reflected off of them. Next up is the properties of microwaves. So in regards to domestic microwaves, Here we have conventional heating, which heats from the outside in, which can obviously create a problem as the inside of a chicken breast might not be cooked thoroughly because the outside cooks before the inside. Here we have microwave, however, that penetrates the food, so it does get to the middle. It's done by an oscillating magnetic field that causes the food molecules to vibrate as they try and align themselves with the moving field. And as you may know, the plate inside the microwave turns. Food is heated up with localized heating in the middle, hence why if you ever have made a microwave meal, you must stir it so that the heat is dispersed throughout the whole food. Microwaves and communication. It's a band of electromagnetic radiation between infrared and radio waves. Microwaves can only travel 30 miles due to the curvature of the Earth. However, with satellite links, this can be extended to hundreds of miles. It's broadcast in all directions. However, a wave itself is unidirectional and travels on line of sight. As you can see here, these are different satellites, and this is kind of how it just gets into the whole big picture of communication. We also have a version of microwave application called Bluetooth. It's a close range microwave application working on line of sight. It has a longer wavelength than infrared, allowing transmissions through walls and other objects. Class 3 Bluetooth has a range of about 10 meters, and it's used for syncing smartphones with other smartphones, computers, wireless headphones, and even cars that have a Bluetooth feature that allows you to go hands-free. Bluetooth could have replaced infrared in many areas, but the technology is not meant to be used for wireless technology networking. Instead, Wi-Fi technology, which uses longer wavelength radio waves, has a larger range, higher bandwidth than Bluetooth, and is the standard that most wireless networking equipment uses. So here we have a comparison between infrared and Bluetooth microwaves. So in regards to orientation, infrared is a direct line of sight. It will not pass through walls, whereas Bluetooth can communicate even when they are separated by obstacles. In regard to security, infrared signals can only be intercepted by a device in its line of sight, whereas the omnidirectional nature of Bluetooth makes it less secure than infrared, even though the protection is coded because many more devices have access to it. The range in infrared is normally about a metre, but can work up to 5 metres depending on the environment, whereas, as we discussed earlier, Bluetooth is up to 10 metres. In regards to connectivity, infrared devices make one-to-one connections, whereas Bluetooth can form networks all at once all the devices have identified themselves to each other and has no limit on how many it can connect to. And versatility, infrared devices such as TV remote controls are designed for specific devices, whereas Bluetooth can work with almost any other Bluetooth device. So next we're on to X-ray imaging. X-rays are in the band of the electromagnetic spectrum between 0.01 nanometers and 10 nanometers. Types of X-ray imaging consist of a mammography, CT and PET scans, and a fluoroscopy. They're used by doctors and dentists to see clear images of broken bones or teeth to identify problems that progress in issues such as dental issues. They can diagnose and monitor medical issues such as kidney stones, bone fractures, foreign objects, osteoporosis, and some tumours are detected by it as well. And it can also help guide medical professions with inserting objects such as catheters, stents, and other medical devices inside of patients. There are, however, some hazards of X-ray imaging. X-rays have an ionizing radiation, which can knock electrons out of orbit, causing changes in molecules that can kill and trigger cancers in the future. One X-ray is the equivalent exposure to natural background radiation for 3 days. We are all exposed to natural background radiation, however, one X-ray is fine as it's just 3 extra days, but over time that will add up. Professionals are exposed daily, and over time the radiation obviously builds up. To protect themselves from ionizing radiation, dosimeter badges are worn, so exposure to dangerous radiation can be monitored and checked to make sure they're within the range, and professionals also stand away, so if you've ever had a dentist x-ray, you'll notice that the dentist may step out of the room or step away from the rays, and also lead vests are worn. So next we're on to visible light. As discussed earlier, it travels at 300 million meters per second to -1, which is also known as the speed of light, and it's notated by a C. White light is made up of the colours of the spectrum of visible light, which is shown here. Here we have the different colours of the spectrum of visible light, their wavelengths and their frequencies. When going through a transparent object, light slows down as it has to make its way through the object's atoms. This causes distortion as the light is refracted. Refraction depends on the material the light is travelling through and the wavelength of the light. White light, when refracted through a prism, creates a spectrum of colours as shown here. And as you'll see, red light is refracted less than the violet light, which is because it has a longer wavelength than the violet. So longer wavelength equals less refraction. Next is filters and pigments. Pigments only reflect certain wavelengths of light, whereas other wavelengths are absorbed. Whatever colour we see is colour wavelength being reflected back at us. Pigments only reflect certain wavelengths of colours. So, as you can see here, this is a green leaf. Green is being reflected. White light is being shone down, but only green is coming up because the leaf is green, and the leaf pigments absorb most of the other colours. It's important to note here that light is energy, and as it is absorbing the other forms of energy, that will be used for things such as photosynthesis. If we had a red apple, red would be reflected. If it was a blue object, blue would be reflected. Filters only allow specific wavelengths of light to pass through, so if you had a green filter, you'll only get green through, and if you had a pink filter, only pink would come through. However, if you had a blue and purple filter, no light would go through as it would block out all the light. As blue would go through the first filter, however that would not be allowed for a second filter as it's not blue. Filters and pigments are subtractive, so when multiple pigments are combined, they subtract a greater number of light waves and create a new colour, whereas transmitted light is additive and combines wavelengths to make white light again, or a secondary colour as shown here. These are the secondary colours, this is the white light, and here if you mix loads of colours together you're likely to get a slushy brown or a black colour because all of them have been combined together. There are many applications of visible light. Anything we can see as visible light, we can use lenses and mirrors in order to redirect and focus light to make our viewing easier. Some examples of uses are periscopes, telescopes, as shown here, microscope, binoculars, fibre optics, which can be used for things such as endoscopes and colonoscopies, lasers, TV and composite colours, and communications. As you can see here, the light comes in from the telescope and it makes the image smaller for our eye to see. So one of the examples I've given is fibre optics. So first, to discuss fibre optics, we need to understand refraction. So when light is refracted, the angle that the light enters the medium affects the angle the light will exit at. So here we have where the angle of incidence is 90 degrees, and obviously the light is just exiting straight. Here the angle of incidence is less than the critical angle and refraction will occur. The angle of incidence is equal to the critical angle, therefore the light is refracted along the boundary, and here the angle of incidence is greater than the critical angle, and therefore total internal reflection occurs and it's just being reflected within the object. Fibre optics are a cable made of glass or plastic, and there is total internal reflection the entire way. So as you can see, it's just being reflected the whole time, and that will keep going until the end of the fibre optic cable. Fibre optics are good as there's less interface than normal ones, and they're also cheaper. Laser is another one of my examples. So it stands for light amplification by stimulated emission of radiation. So laser works by stimulating atoms in an amplifier medium. The electrons in the medium then jump between energy levels to emit light at a specific wavelength. Light is then reflected back and forth within the amplifier medium, and it will gain energy and therefore become brighter. Laser waves are monochromatic, so they're a single colour or wavelength. They're coherent, so they all travel in phase. They're non-divergent and the beam doesn't spread out. Laser can be used in communications, printing, so the laser draws an image of positive charge on the printing drum, which then attracts a toner powder, which obviously then goes onto the paper. It can be used in medicines to make insertions, laser eye surgery, or destroy kidney stones. So ultraviolet light and fluorescence. UV is between visible light and X-rays at a wavelength of 400 nanometers to 10 nanometers. We cannot see UV light, however some animals and fish can. Fluorescent objects absorb UV wavelengths and then emit another wavelengths within the visible spectrum that the eye can detect. Some objects occur naturally, such as rocks, however other fluorescent objects are manufactured. So here I have a diagram of what happens when a object fluoresces. So UV light is given, gives more energy, and then the electron slowly loses energy and emits a low energy light wave. And that is the fluorescence that you are able to see. So there are many types of UV. There's 3, UVA, UVB and UVC. So in order to go a bit further, we need to understand that a photon is a minute energy packet of electromagnetic radiation, and each packet of energy has a specific wavelength, frequency and therefore characteristic. So UVA is within 400 nanometers and 312 nanometers, has low photon energy, it's visible to animals and fish, it has a long wave of black light and it passes through the ozone layer. UVB is 315 nanometers to 280 nanometers, it's a medium wave and it's mostly absorbed by the ozone layer. UVC is between 280 nanometers and 100 nanometers, it's a high photon energy, short wave, and is completely absorbed by the ozone layer and atmosphere. There are many applications of ultraviolet light, such as fluorescent pigments such as high visibility shirts, day-glow paints on banknotes, where UV is then shone on it and then it will fluorescent. So banknotes, that is used to make sure that they're real. Crime scene investigations, it's used to detect bodily fluids such as blood, saliva or fingerprints, as they will fluorescence in the presence of UV light. Some objects are also marked with visible ink in case they're stolen, such as bikes. So in order to return it to its rightful owner, the bike may be scanned to see if there's any invisible ink, and if their code is right, it will be returned. And also some narcotics such as cocaine is fluorescent. Ultraviolet light is also used for UV sterilisation, which is used in hospitals, for food processing and air purifying plants to destroy potential pathogens. And here you can see UV light being used on a crime scene in order to see any fingerprints or bodily fluids on the crime. There are biohazards of infrared and ultraviolet radiation. In infrared radiation, it will heat up anything it strikes, and if powerful enough, will cause superficial burns and blisters to skin tissue. But you're at more danger of burning yourself by actually touching the hot object. Focused and intense infrared radiation can cause damage to the cornea and retina in the eye. In regards to ultraviolet radiation, it's much more dangerous than infrared radiation. It's a higher frequency of electromagnetic radiation and therefore carries more energy and can penetrate further. Too much sun or UV can penetrate cells and cause chemical changes in the DNA, possibly resulting in mutations and cancer. Some UV light, however, is beneficial as it stimulates the production of vitamin D. Vitamin D has positive benefits on blood pressure, the immune system and bone growth. Thank you very much for watching my presentation on the electromagnetic spectrum. Hope you enjoyed it, and here are some references that I have used throughout my presentation. Thank you.